Welcome to this online training about the Intel FPGA Power and Thermal Calculator for Intel FPGA devices. My name is Steve. This training is available for desktop viewing as well as in a format compatible with portable devices, both available from the same link included in your registration email. For either version, while watching the training, use the controls at the bottom and side of the screen to navigate to any point. Feel free to pause the training at any time to experiment with the software. When you're done with the training, please use the link provided in the registration email you were sent to provide us feedback on the training and ways in which it can be improved. I'll remind you about that later. This training focuses on the basics of power analysis and the use of the Power and Thermal Calculator, or PTC. By the end, you'll understand what is meant by static power and dynamic power usage. You'll learn how the PTC is used to analyze both. The PTC is your main tool for performing a quick analysis of power usage at any stage of a design. You'll learn how to set up and use the tool to do this. You'll also see how the tool can be used to calculate the thermal factors necessary for implementing a successful cooling solution for your design. The PTC takes into account the unique multi-die design of Intel Stratix 10 and Intel Agilex devices to provide a complete solution for power and thermal analysis. Here's the agenda for this training. We'll start with a look at power analysis in general and the factors involved in measuring power in an FPGA device. We'll then look in detail at the tools available in the Intel Quartus Prime software related to power analysis and then focus on the PTC. Finally, we'll look at how to use the PTC to perform a thermal analysis. If you are already familiar with the basic concepts of calculating power and the factors involved in estimating power usage in an FPGA design, feel free to skip ahead. Let's start with a look at power analysis in general regarding FPGA designs. At a most basic level, what is power? Wikipedia provides a formal definition of power as the rate per unit time at which electrical energy is transferred by an electric circuit. The unit of power is the watt, which can be calculated at its most basic level as the current through a circuit multiplied by voltage, the electromotive force. All tools and analysis are based on this simple formula. Remember, power is as easy as pi. With that in mind, when we want to analyze and optimize power usage in today's high-performance FPGA designs, what are our biggest concerns and challenges? Increasing device densities and performance make power consumption considerations more important than ever. Today's larger devices can implement much more of a system's overall functionality, including many high-speed applications that were unheard of only a few years ago. With devices running at higher speeds and performing these more advanced functions, more power is required and consumed. There are many challenges regarding power when creating such a design. Early in the design flow, it's necessary to estimate system power usage to determine power supply and cooling requirements. This can be difficult to do, especially with an FPGA design that can change just by reprogramming the chip. Supply components must be considered along with the board space required to lay out those components. A cooling solution must be selected that must be robust enough to prevent thermal damage to components. With power supplies chosen, the design must stay within a fixed power budget. Going outside of this budget is not an option, since it could require redesigning the power supplies and cooling solution. At the same time, the system must meet a cost budget. Bigger power supplies and cooling hardware add to this cost. If power usage can be reduced, the overall system cost can be reduced as well. The system must also be reliable. The more fans and cooling hardware required, the more likely something could fail. Finally, the design cycle must be as short as possible. Development schedules are tighter than ever, and a lengthy design cycle just to meet power and thermal requirements is not acceptable. To meet these challenges, three main things are needed. First, you need to close on the design of the system power supplies and cooling solution as early as possible in the design cycle. This will help speed overall system closure. Next, you need to make sure that the design meets the power budget set for each power supply later in the design flow when the design is near or reaches completion. Finally, you need to be able to increase design efficiency and productivity to shorten the design cycle as much as possible. What tools can you use to meet all these needs? Intel FPGA provides the tools you need to close power in your system. At any point in the design cycle, use the Power and Thermal Calculator, or PTC, to model your power requirements and calculate what kind of cooling solution is required for your design. The PTC is an easy-to-use what-if analysis environment that can be used as a standalone tool or while using the Intel Quartus Prime software. With the information reported by the PTC, you can choose and start designing the system power supplies and cooling solution, meeting the need of fast system closure. Later in the FPGA design process, use the Power Analyzer built into the Intel Quartus Prime software to generate highly accurate estimates of power usage based on a design's actual resource usage, along with its placement and routing in the chip. This helps you meet the second need, meeting the power budget of the design. Finally, use the automated power optimization options available to automatically reduce power usage in your design. These options are simple to implement, meeting the third need, increasing your overall design efficiency and productivity. To understand how a power analysis of an FPGA design works, you must first understand power usage in FPGA devices. When the device is first powered up and programmed with a design, the current usage ramps up until it reaches its static level of power usage. Static power is the current drawn by device resources that are not clocked by a user design. This includes leakage from all FPGA functional block resources. Static power excludes the DC bias power that gets consumed by the device's I/O pins and analog transceiver resources. This separate power usage is referred to as the device's standby power. Finally, when the device is in normal operation and the design is being clocked, dynamic power is added on to the overall device power usage. Dynamic power is the additional power used by the design as it is clocked. Dynamic power consumption, and therefore total power, varies greatly from design to design, but is based on operating frequency, resource utilization, and other factors. It's important to understand power usage in FPGA devices over time, from initial power on to normal user mode. When the device is first powered up, the current usage ramps up, as shown here, until it reaches its static level of power usage before device configuration. Device configuration occurs at some point during the time labeled as static. In this diagram, the static section shows the power consumption of the device if no clock signal were applied. Clocks are held in reset during this period of time. Next, and most importantly, clocks are released and the device enters user mode. This is the normal operating power usage of the device. As mentioned, operating power usage is a combination of static power along with I/O and dynamic power. In this state, the system clock is oscillating and the design is operating. So what are the differences between dynamic and static power? Once a design is complete, static power does not generally change with resource utilization. However, it is still affected by what operating modes are selected for particular resources and by I/O usage. Static power is also affected linearly by device selection and process variation, but exponentially by operating temperature. A device with more logic includes more transistors and thus will naturally use more static power. Be sure to check your selected device's datasheet for details on static power use. A device operating in a higher temperature environment without proper cooling raises junction temperatures and can greatly increase static power. An effective cooling solution can help with this. When designing power supplies, be sure to use the worst-case static power specifications for your selected device and operating environment. As mentioned, dynamic power varies from design to design. As such, dynamic power can be a more controllable power component to consider when creating a low-power FPGA design. The equation shown here illustrates this. Dynamic power is affected by the capacitive charging of transistors in the device, the momentary short circuit power that is expended when a transistor switches, the operating frequency of the design, and the number of flip-flops switching each clock cycle, referred to here as the circuit activity. Looking at the equation, the only factors a designer can affect are the operating voltage, the operating frequency, and signal activity. The device can be run at a lower operating voltage, or the design could be run at a lower operating frequency. But reducing signal switching activity in a design is the single best way to reduce overall dynamic power. Signal activity, as it relates to dynamic power, is defined by two main factors. Toggle rate, defined as a percentage, refers to the average number of times a signal transitions in a second, or relative to a clock. Toggle rate can also be expressed in signal transitions per second. Toggle rate is typically less than 50%, since it is rare for signals in a design to toggle most or all of the time. However, extra factors, such as signal glitching, may cause an artificial increase in toggle rate. The toggle rate of a signal is the key factor in making an accurate estimation of dynamic power usage. Dynamic power increases linearly as the toggle rate increases. In the PTC, signal toggle rates default to 12.5%. This corresponds to the toggling of the output signals of a 16-bit counter. Static probability, defined as a fractional value between 0 and 1, refers to how much of a defined analysis period a signal remains at logic high. The analysis period is usually based on the duration that is needed for a test case to fully exercise the normal activity of the signal. At the extremes, a static probability of 0 indicates the signal is at ground for the entire duration of a test. Conversely, a 1 indicates the signal remains high for the duration. Static probability affects static power on I/O. For inputs, it affects the power usage of the logic and routing fed by the inputs. This is due to state-dependent leakage into the device. On outputs, resistively terminated I/O standards consume power depending on the level of the signal. Before continuing, it's important to understand a little bit about the unique architecture of Intel Stratix 10 and Intel Agilex devices. While previous devices, like those in the Intel Aria 10 family, follow a more standard architectural design, Intel Stratix 10 and Intel Agilex devices feature an advanced architecture, referred to as the Intel HyperFlex architecture. Intel Agilex devices feature the second generation of the Intel HyperFlex architecture after it was first introduced in Intel Stratix 10 devices. A traditional FPGA architecture consists of several basic building blocks: memory, DSP, and logic array blocks, or labs, along with the routing wires that connect them together. Labs consist of adaptive logic modules, or ALMs, that allow you to build any type of logic function, along with registers for temporary data storage. A traditional FPGA includes thousands of available registers. However, the Intel HyperFlex architecture takes this further by including additional registers throughout the device's core fabric. The key building blocks for the architecture are bypassable hyperregisters located in every routing segment and at all block resource inputs. These hyperregisters, along with the traditional registers found in the ALMs, can either be included in a circuit path or bypassed selectively. With all these additional registers and the software tools to support their selection and inclusion in a design, the Intel HyperFlex architecture provides a fine-grained approach to the use of registers, because hyperregisters are essentially located everywhere throughout the core fabric. But what about the power used by all these additional registers? As far as static power is concerned, the hyperregisters are implemented as simple D flip-flops. Each one requires only a few transistors to implement, fewer than the number required to implement an ALM register, and much fewer than more complex resources like the RAM and DSP blocks. As a result, the hyperregisters collectively contribute minimally to the total static power, less than 1%. With regards to dynamic power, as with other resources, hyperregisters on their own do not cause an increase in power. During design optimization, the compiler takes register stages already implemented in ALM registers and replaces them with hyperregisters. As such, the signal activity has simply moved from the ALM registers to the hyperregisters. The use of the hyperregisters proves to be more efficient than using the ALM registers when implementing optimization methods such as retiming and pipelining. Keep in mind, though, that through these optimizations, the hyperregisters do enable designs to run faster, and that increasing the clock speed of a design causes dynamic power consumption to scale with that increased frequency. Compared to Intel Stratix 10 devices, Intel Agilex devices' process technology also plays a part in reducing power. First, transistors are tuned for power based on their intended usage. For example, for device resources that don't require high performance, such as configuration blocks, the transistor leakage in those blocks is reduced. Second, a custom metal mix for manufacturing is used to reduce capacitance. Recall that in power calculations, such as the equation for dynamic power discussed earlier, power consumption is directly proportional to capacitance. So by reducing capacitance using this custom metal mix, the overall power consumption of the device is lowered. Intel Agilex devices use a 10 nanometer process technology. By moving to a smaller technology, the nominal voltage can be lowered, which lowers power. This, in conjunction with process tuning, enables lower power binning. Finally, many variants of Intel Agilex devices support the Smart Vid feature, where the device can provide information to an adjustable voltage regulator to automatically adjust core voltage as needed. While this is available in some variants of Intel Stratix 10 devices, many more Intel Agilex devices support Smart Vid. We'll discuss this feature in more detail later. In addition to changes in the manufacturing process, changes have also been made to the device itself to lower power use. The transistors and the number and type of routing channels were redesigned to reduce power. This includes new technology to reduce the leakage of the channels and leave unused channels floating. These changes help to reduce the dynamic power consumed by the routing. Intel Agilex FPGAs also have additional power management features that reduce power consumption. Power can be gated to unused resources such as DSP blocks and memory blocks, including M20K blocks and the ESRAMs in device variants that include them. M20K blocks also have their own lower power modes. Finally, unused transceiver tiles can be disabled or completely powered off. Let's now take a look at the tools available for performing a power analysis on an Intel FPGA design. Now that we've defined the different types of power usage that must be analyzed, we can see how the Intel power analysis tools fit in. As mentioned, the PTC is a graphical tool that estimates power usage based on entered design information. As such, it can be used at any point in the design flow, though typically before or during early development. The accuracy of the PTC is reliable, but lower than the power analyzer. To calculate both dynamic and static power in the PTC, you enter known information about the design into the tool. For dynamic power, you provide estimated resource usage and clock toggling information. For static power, you provide information about the target device selected and the device cooling solution. The PTC can be downloaded as a standalone tool or as part of a full installation of the Intel Quartus Prime Pro Edition software. The Power Analyzer tool is found in the Intel Quartus Prime software, both standard and pro. It is meant to be used on a design that is finished or nearly finished, but can be used at any point once the design is compiled to provide power estimates as a guide for performing power optimization. The Intel Quartus Prime software Power Analyzer creates highly accurate power estimates that are based directly off the FPGA design. Static power analysis is performed using input values similar to the PTC. For dynamic power, exact resource usage is known from the fitter, and signal activity information can be provided directly as a user-entered toggle rate or through the results of a design simulation. Including simulation results provides a much more realistic picture of signal activity, making dynamic power estimates much more accurate. Note that the Intel Quartus Prime software does not support gate-level timing simulations for Intel Stratix 10 or Agilex devices. This diagram illustrates the typical use of the available power analysis tools over the course of a project design cycle. Early in the design cycle, during the design concept stage, the PTC is used to start getting estimates of power based on information entered manually into the tool. Once the design is created in the Intel Quartus Prime software, a design profile can be generated and imported into the calculator, providing a more accurate early power estimate. During the main design phase, you can continue to use the PTC and more accurate design resource usage information to get good estimates of power at any point. Once the design successfully compiles, use the power analyzer to get more accurate estimates, now based on actual placement and routing results from the fitter. Finally, at or near design completion, simulation results can be provided to the tool to incorporate accurate signal toggle rates and static probabilities to get the most accurate estimate. You can continue to use the results from the PTC as a baseline for future designs. So just how accurate are the tool's estimates? How confident can you be with the results in making power-related decisions, such as the design of your power supplies? Power estimates are only as good as the power models used to describe a device's power usage. To that end, Intel uses a rigorous modeling methodology where detailed circuit models are created using HSpice. All models are then tested and calibrated against the actual device silicon. To further guarantee the accuracy of the models, power estimates are performed on the models using a variety of actual user designs. Even with highly accurate power models, the power estimates provided by the tools are only as good as the information that is provided to them. For example, are toggle rates accurate? Does the signal activity information model real-world operation of the design? Is the count of resource usage, such as the number of logic elements used, accurate for the design? The more accurate the information, the more accurate the estimates. 3 power model types are available depending on the target device selected. Advanced and preliminary models allow you to perform an early power analysis on devices that may not be available yet for purchase, but are available for starting a design in the Intel Quartus Prime software. Advanced models are the earliest models available based only on simulation results. Preliminary models use post-layout simulation results along with correlation with actual silicon. Both advanced and preliminary models are subject to change after further characterization. Final power models will provide the most accurate results since they are tested and correlated with final silicon and actual designs. These models are not expected to change in future versions of the software. The Intel FPGA power and thermal calculator always indicates the stage of the power model for the targeted device. If you are using a device that has a final power model, the PTC is expected to provide results within 15% of what you would see for the highest power rails on a real device on a board. This accuracy assumes accurate design inputs have been provided to the tool. The report generated by the tool will include recommended margins for designing your power and cooling solution, taking this accuracy into account. For the power analyzer, the results are expected to be within 10%, again assuming accurate information has been provided. To learn more about setting up and using the power analyzer, see the e-learning and documentation linked here. Now let's take a look at how to use the PTC to perform an early power estimate of a design. The PTC allows you to perform early estimates of power even before a project or any design files have been created. If a project is available, accurate information from the project itself can be exported from the Intel Quartus Prime software and imported into the calculator to save time when entering resource usage information. This also provides a more accurate power analysis since the information comes from the design itself instead of your own estimates. The PTC also provides information about device thermal management and cooling solution requirements based on a selected maximum desired junction temperature. For detailed information about the PTC, see its user guide. The latest version as of this training is linked here. The PTC can be directly launched from version 19.4 or later of the Pro Edition of the Intel Quartus Prime software, or run as a standalone Windows or Linux application, avoiding the need for a full installation of the Intel Quartus Prime software. You can download the standalone PTC from the Intel FPGA Download Center as indicated here. As of version 20.3, no additional licensing is required to use the PTC with either Intel Stratix 10 or Intel Agilex devices. The PTC is easy to use. Enter into the tool as much of the listed information as you can. You can enter in information manually based on your specific requirements and estimated resource usage, or through a file generated from the Intel Quartus Prime software. The more accurate and complete the information, the more accurate the power estimates will be for your final design. As information is entered, report information is generated that provides estimated power consumption for the device and the design. The calculated information is organized to provide power usage for each type of device resource and power requirements for each supply. As changes are made to the input data, the calculated values update on the fly, providing a true what-if analysis. The PTC can also provide a detailed thermal report that accounts for the supported device family's multi-die architecture. Previous devices used only a single monolithic die, where heat was equally distributed and left the device uniformly. As such, there was only a single junction temperature that defined the device's thermals. Because Intel Stratix 10 and Intel Agilex devices have multiple dies for the transceivers and, in some cases, high bandwidth memory, there is a non-uniform distribution of power and heat. Each silicon die has its own power usage and thus also has its own junction temperature. The different die areas cause heat to leave each die at a different rate. Thus, thermal management in these devices must ensure that each of these dies are below the specified operating temperature, and the overall thermals are defined by which silicon die heats up first. This advanced model uses a new thermal modeling term called SciJC. SciJC is best used to describe thermals for multi-die implementations that have a non-uniform distribution. SciJC is a dynamic value that is dependent on the application power and is influenced by multiple silicon dies. As such, multiple values are possible. The PTC reports SciJC values for each die based on the design implemented in the device and the effect of multiple dies. The report provides a breakdown of power between the transceiver tiles and the core die. The tool calculates SciJC specific to your design. A SciCA value is also reported as a goal for the design of your cooling solution. SciCA defines the total cooling solution required to keep the device's junction temperature at or below the maximum operating temperature of the device. You can use these values reported by the tool to easily experiment with different transceiver settings and placement to reduce power usage and simplify the cooling solution. To learn more about thermal management and how the older early power estimator and now the newer PTC can help in designing a cooling solution, see the separate Intel Stratix 10 thermal management online training linked here. The basic thermal management factors discussed in this separate training are applicable to all devices supported by the PTC. We'll look at setting up and performing a thermal analysis with the PTC in more detail later in this training. The file types listed here are used with the PTC. First, a .ptc file is the main file type used to store all the settings input into the tool and all calculated results based on those inputs. Use it for backing up the information you've entered into the tool and for moving that information into a different version of the tool if necessary. As mentioned, you can generate a file from an Intel Quartus Prime project that provides detailed, accurate resource usage information for the PTC. This file type has the extension .qptc. Finally, the PTC supports importing resource usage information from a .csv spreadsheet formatted file. Older versions of the Intel Quartus Prime software and the older Early Power Estimator tool generate this file type. To get started using the Intel FPGA Power and Thermal Calculator, open the standalone version of the tool or access it from the Tools menu in the Intel Quartus Prime software, as mentioned earlier. When you start the tool, you can either open an existing .ptc file or start a new analysis by selecting the appropriate device family. If you select a .ptc file, the device family will be selected for you based on the information in the file, but you can override the family selection to analyze power usage in a different device family with the same resource usage information defined in the file. If you enable the override, select the device family to use for the analysis. If you open the calculator from an open Intel Quartus Prime project, the targeted device family in the project is selected, and basic information about the targeted device will be filled in automatically. Prior to version 20.3, the PTC consisted of multiple tabs where you could enter information pertaining to your design and view output generated by the tool. Here's what the tool looked like. The rest of this training will focus on version 20.3 and later, but even if you are using an older version of the tool, the process for using it is basically the same. Here is what the PTC looks like in version 23.3. Again, the interface may look slightly different in the version you are using, but the basic setup and use is the same. The main difference from the older versions is that the resource usage tabs are now separate pages selected from the indicated Power Summary and Navigation window. Click a listed resource to access that resource's page, or select a resource page from the View menu. All windows in the tool can be resized, moved, and closed. Open or reopen any windows from the View menu. To use the tool, first specify basic information about the target device and how it will operate here on the main page, using pop-up lists as needed. This information includes the selected part number and the device grade. The parameter table in the main window lists the total number of resources available in the selected device, as well as the status of the power model as discussed earlier. You'll also want to set the power characteristics option appropriately. To design power supplies and cooling solutions for worst-case power usage, set this to maximum. Maximum also lets you select from a number of different calculation modes for the thermal analysis. We'll look at these modes later. If you want to perform just a power analysis on the device without a detailed thermal analysis, leave the power characteristics set to typical and specify a fixed junction temperature as shown. Once the main page is complete, go to each of the other resource information pages and enter as much information as possible about the different resources used in the design. On each page, discussed in detail later, specify logic resource usage, including ALMs and flip-flops, RAM and DSP blocks, clock domain properties and used PLLs, I/O and I/O-related IP cores, and transceiver block use and configuration. You can also specify CPU core usage when using a device variant that includes the hard processor system. Other pages may be available depending on the target device selected. You can enter information into any white or light gray text input fields. Grayed out input fields indicate fixed or single value input fields that cannot be edited. Dark gray fields and reporting windows, such as the Power Summary window, indicate output values calculated by the tool. When you have finished entering all the information about your design, switch to the Report page to view a per-rail power estimate. Common options are available in a toolbar at the top of the PTC. The IP wizard, also available from the File menu, lets you easily add resource usage information to the calculator for commonly used IP. The wizard presents a list of IP available for the targeted device. Different IP are listed depending on the device selected. Choose an IP and fill in a subset of the IP's parameters. For example, for a DDR4 external memory interface, you would only need to enter basic information, such as the address bus width and the memory clock frequency. The required resources are automatically added to the appropriate resource usage pages of the PTC. Power usage for an IP added through the wizard is visible on the IP Power Summary tab of the Hierarchy Manager, discussed in a moment. The Select Device option allows you to change the targeted device for the calculator at any time. This is also accessible from the main page and the device selection window, which you can open from the View menu. You can change the device to any device in the currently selected device family. You can't change families without creating a new instance of the PTC. If you want or need to do this, save the current calculator settings in a .ptc file and open that .ptc in a new instance of the tool, overriding the selected device family as shown earlier. The Recalculate mode lets you choose when the PTC updates calculated output fields. If it's set to automatic, output is updated as soon as you add information or make any changes to existing information in the calculator. If you are setting up a new calculation or making many edits to settings in the calculator, it may be helpful to set this to manual to avoid having to wait for the tool to recalculate every time you make a change. In manual mode, a recalculation needed warning will appear after you've made any changes. Click the indicated button to manually recalculate. To more accurately reflect power usage across your design, you can set up a design hierarchy in the PTC, similar to how instantiated entities are organized in the Project Navigator in the main Intel Quartus Prime software. With a design hierarchy, the PTC will report total power usage by the design, but also provide a breakdown of power by resources used in each hierarchical level. A design hierarchy is created in the PTC by either opening or importing a .ptc file that already includes a hierarchy, or by specifying hierarchical levels and entity names as information is added on each resource usage page. In the example shown here, a 3-level hierarchy is created by adding hierarchical level names separated by pipe characters on a resource usage page. The entity names indicate which entity at that level of the hierarchy is using the resources specified. We'll look at how to do this in more detail later. Once a hierarchy is established, you can perform a number of useful actions in the Hierarchy Manager. Export a .ptc containing resource usage information for a selected hierarchy level and all its children for use in a different calculation. Duplicate a level to set up resource usage for a separate but identical branch of the hierarchy. You can also rename levels. Any changes or additions are immediately reflected in the appropriate resource usage pages. One additional feature of the Hierarchy Manager is the ability to bulk edit resource usage and other options from multiple hierarchical levels simultaneously. Normally, you would need to manually create multiple entries on the resource usage pages to do this for each level. However, you can simplify this process by first creating normal entries on the resource usage pages, targeting a particular hierarchical level. With the targeted level now appearing in the Hierarchy Manager, select it, click Bulk Edit, and enable the Apply to All Child Instances option. The tool displays resource usage pages and settings common to the selected level and any child levels. Enable and set resource usage and options for any of the listed items and click Apply. The bulk edit window indicates what was edited and the resource usage pages immediately reflect the changes or additions. Now that we've looked at the basic graphical elements for using the PTC, it's important to understand when and how to use the tool during the FPGA design process. The PTC should be your first main tool for performing a power analysis. As mentioned earlier, you can use the PTC at any point during the design flow. Let's look at how the PTC is used at three main phases of a design: before starting the design, during the creation of the design, and after the design is complete. Before even starting a design, you can use the PTC to get power estimates based on what you think will be in your design. The reported results are averages based on the input information you provide. You can easily play around with the information you enter into the tool to get a true what-if analysis for your future design. Again, the power numbers you'll get are only as accurate as the information you provide. So at this stage of the design process, use the output from the PTC as good ballpark figures to get started in designing your power and cooling solution. To continue adjusting the input information you've provided and to back up what you've done, save the current state of the calculator as a .ptc file. Any information entered into the PTC can be saved as a .ptc file. You can back up this file if you plan on making changes in the PTC, or you can save a new .ptc file from the tool. Making a backup like this is helpful if you want to experiment with making a change in the tool that could affect the entire power analysis, such as a change in device. Create the .ptc file, make the change, and then open the backup .ptc file if you don't like the results. Creating a .ptc file is also useful for easy sharing of PTC results. Share a .ptc file, and any user can open the file in the same version or a newer version of the tool. To continue a previous calculation, simply open a .ptc file from the File menu. A new instance of the PTC will open with the information from the .ptc file filled in. Be sure to review any warnings that may appear, especially when moving to a newer version of the tool. You can edit the information entered from the .ptc file and overwrite the existing file, or create a new file with your changes. The second phase for using the PTC is while you're actually creating the design. As before, you can still manually add information about your design to the tool at this point, but you can also import design information directly from the Intel Quartus Prime software via a .qptc file. This simplifies the process of entering information into the tool and provides a more accurate power estimate because the numbers will be based on your actual design. You can start a new calculation based off the data in the .qptc file, or you can append selected information from the .qptc file to your existing power calculation. You can still add, change, or remove resource information from the PTC as you like after the import to see the effect on your design's power usage. Note that if you experiment with a major change to your design in the PTC, such as a change in device family or using a different device package, you should add margin to the PTC results. The PTC will still be analyzing based on the resource usage from before the major change was made, so the reported numbers will be less accurate. At some point, you'll want to make the same major change in the Intel Quartus Prime project, recompile the design, and import the updated design information into the PTC. Design-specific resource usage is provided to the PTC using a .qptc file. The file is generated with a default name of the project name automatically whenever the power analyzer is run, but you can set a custom name for the file, either by adding the assignment shown to your projects.qsf file or by setting the name in the power analyzer settings. The project must be fully compiled and the power analyzer run to generate the file. You can run the power analyzer manually from the processing menu, or enable the option shown in the project settings to run the power analyzer automatically during a full compilation. To learn more about configuring and using the power analyzer, see the separate e-learning linked to earlier. To use the .qptc file in the PTC, simply open it in the tool from the File menu. The PTC will also automatically open a .qptc file if the tool is opened from within an open project, and the .qptc file for that project is found in the project directory. Note that if you manually open a .qptc file, any manually entered information in the tool will be overwritten with the design-specific information from the Intel Quartus Prime project. To avoid this, you can instead append information from the .qptc file to the existing PTC information using the Import Design option. With Import Design, you can select exactly what resource information you want to bring into the PTC from the .qptc file. You can also choose to partially or fully flatten the hierarchy of your imported design, combining the power usage of multiple hierarchical levels of your design into fewer levels to simplify the design's representation in the PTC. See the PTC user guide for details on using the Import Design command. Once you've opened or appended the .qptc file, you can manually add to or adjust any of the imported resource usage information. Whether you adjust the .qptc information or not, save the PTC settings and analysis as a new .ptc file for future use. If you are thinking about moving a design from an Intel Stratix 10 device to an Intel Agilex device, you can bring a .qptc file from an Intel Stratix 10 instance of the PTC to an Intel Agilex instance of the tool. To do this, first create a .ptc file for the Intel Stratix 10 design. Then, launch a new instance of the PTC, choosing to open the existing .ptc file just created and enabling the Override Family in Design File option. Select the target Intel Agilex device you want to use and proceed to use the previously entered resource usage information. Note that you cannot take an Intel Agilex.qptc file and import it for analysis on an Intel Stratix 10 device. The Intel Stratix 10 PTC supports the use of older .csv formatted files that were generated by version 19.4 of the Intel Quartus Prime software and the Intel Stratix 10 Early Power Estimator, or EPE. If you want to use this older format file, open the .csv file in the tool, add to or edit the resource usage settings as desired, and save as a .ptc file. Note that this does not work with any older versions of the EPE, but you can bring older version .csv files into the 19.4 version of the EPE, create a 19.4 version of the .csv, and then bring that file into the PTC. The final design phase for using the PTC is when your design is complete. Even when you are finished with your design, you can still use the PTC to compare the design's actual power usage with the tool's estimates. You can also use the results as a baseline for future designs, making adjustments in the PTC to meet the needs of that future design. Again, to do this, simply import a .qptc file generated from the completed design project. This will be the most accurate representation of the resources used. However, note that only toggle information provided as assignments in the project will be included in the analysis. Of course, once the design is complete, use the Power Analyzer instead of the PTC to get the most accurate analysis for the current design. Here is a summary of the use of the PTC at the 3 design stages just mentioned. Again, the further along in the design, the better and more accurate the analysis will be. But there's no reason not to make use of the tool no matter how far along you are in your design. Now let's take a look at each of the pages in the PTC and some key inputs that should be provided to get the most accurate power analysis. Let's start with the Logic page. Select the page using the View menu or by clicking Logic in the navigation window. At the top of the page, the Summary section summarizes the information entered on this page and the power used by this particular resource. You'll see similar summaries on other resource usage pages. The Power Rail section breaks down the power usage for this resource by rail. For Intel Agilex devices, this section is dynamic, displaying only the power rails that supply power to the resources on this page. For Intel Stratix 10 devices, all power rails in the device, even if they do not power this resource, are always displayed. Like the main page, information is entered into the white or light gray cells. On this page, each row represents a design entity, allowing for a breakdown of resource usage and toggle rate for each part of the design. Entering information in the bottom empty row automatically adds additional rows for entry. For each row, optionally enter design entity names and their location in the design hierarchy, using the pipe character as a delimiter to indicate the estimated or actual number of logic resources used by that part of the design. Remember that the hierarchical levels you enter here and on any other resource usage page can be managed in the Hierarchy Manager window, accessible from the View menu if it's not visible. For the resources themselves, enter in the total number of registers, along with twice the number of ALMs used by the module. Half ALMs are used because two separate functions may be placed into a single ALM. If the design has already been compiled and you didn't import a .qptc file, you can find these values in the Place Stage section of the FITR report in the compilation report under Resource Usage Summary. Enter a clocking frequency and toggle rate for the logic. As mentioned earlier, a default toggle rate of 12.5% is set for all design resources. Design simulation is the best way to select an accurate toggle rate. Finally, you can experiment with a higher or lower routing metric value instead of the default of 3. The selection of a routing metric is based on fan-out and the amount of routing resources used. A higher value represents more routing resource power usage. Importing a .qptc file will provide the most accurate value for this. As input values are entered, output values in the dark gray cells update to provide routing and logic block power usage for the design. Moving to the on-chip RAM page, rows represent design entities with all identically configured RAM. Once again, you can specify particular RAM implementations as design entities and their location in the design hierarchy. First, set the RAM type. Different devices may support only certain types of RAM blocks. If the design has been compiled, this can be found in the FITR RAM Summary section of the FITR Place Stage report. Next, set the number of RAM blocks, the RAM data width, and the RAM depth. The number of blocks should be specified as the number of logical blocks that make up the RAM, not physical blocks. This is because more than one physical block may be used to implement a larger logical memory. Based on the number of logical blocks specified, the PTC can figure out what the minimum physical block usage would be, which corresponds to the amount of power used by the block resources. The vertical network options refer to the use of M20K blocks with the hardened NOC found in Intel Agilex 7 M-series devices. See the Intel Agilex 7 FPGA NOC user guide, linked at the end of this training for details. Specify how the memory is set up by choosing a RAM mode, and then enter the RAM port clock frequencies and enable signal active percentages. Dynamic power is consumed only when the memory is enabled and clocked, so power can be saved by occasionally disabling the entire memory or just the read or write functionality. Again, the vertical network port options only apply to M20K blocks used with the NOC in Intel Agilex 7 M-series devices. Finally, the toggle percentage represents the toggle rate for the output signals of the memory. 50% indicates that half the time the memory output is not transitioning. This is the largest value that makes sense for a RAM. Like the RAM page, each row of the DSP page represents either an entity where all DSP instances are configured the same, or represents a specific DSP inferred structure or IP. First, specify the DSP configuration. There are many options available. As usual, if the design is already compiled, check the compilation report to see how any used DSP blocks were configured if you're not sure. Next, set the number of instances to the number of DSP instances that all have the same configuration, clock frequency, toggle percentage, and register usage. Multiple instances can be implemented in a single DSP block, so this does not necessarily equal the number of DSP block resources used in the design. As with RAM, set the clock frequency, clock enable active percentage, and the output toggle rate. Enable the pre-adder and coefficient options as needed. Finally, set the number of registered stages for the DSP module. The value to use here depends on the selected configuration, so see the PTC user guide for details on what value to select. Rows on the clock page represent each clock network or separate clock domains in the design. Note that you do not need to specify what clocking resource is being used for a particular domain. While Intel Stratix 10 and Intel Agilex devices have global, regional, and periphery clock networks, the PTC does not distinguish between them due to the minimal differences in each one's power usage. The fields on this tab are relatively self-explanatory. The clock network fanout can be obtained from the global and other fast signals summary report in the fitter place stage report. Like RAM and DSP, set the enable active percentages for each clock. Gating an entire clock network, or at least the local part of a clock network driving particular logic array blocks, can have a significant impact on dynamic power usage, since unclocked resources use little to no dynamic power. Finally, the utilization factor for a clock is similar to the routing metric value for logic. A higher utilization factor indicates that the clock is more spread out over the device and has a higher fanout. Again, you can stick with the default value of 2 or experiment with higher or lower values. As mentioned earlier, Intel Stratix 10 and Intel Agilex devices feature hyperregisters throughout the architecture. When the PTC calculates register power usage, whether they are registers in the ALMs or hyperregisters, it analyzes both the toggling of the clock and data signals. For hyperregisters, data signal power is pretty much the same whether the hyperregister is enabled or bypassed. Since hyperregisters are mostly located in device routing, hyperregister power usage is lumped into the power usage of the routing where it is located. This is handled automatically by the tool. As such, the use of hyperregisters should not be included in the number of flip-flops column on the PTC's logic page. If you are using the PTC before creating a design, you would not know hyperregister resource use anyway, because the use of hyperregisters is determined late in the compilation process. For the power used by clocking hyperregisters, the separate clock page, as just discussed, is used. On the clock page, you can specify the total fanout for a particular clock domain. The higher the fanout, the more resources are being clocked, thus increasing dynamic power usage. As such, you can include hyperregister use in the total fanout column on the clock page. You can set this option accurately by getting the actual fanout number from the global and other fast signal summary report as mentioned. The PLL page is relatively self-explanatory as well. Each row represents one or more PLLs in the design with all the same properties. Set the PLL type to either a PLL driving the I/O banks or feeding the internal device fabric. Some devices may include options for additional types of PLLs. Specify the number of PLL instances, the number of counters, and the operating frequency. For Intel Agilex devices, specify an I/O bank ID for the location of the PLL. This affects utilization and provides a more accurate thermal analysis. As mentioned earlier, the IP wizard can automatically fill in resource usage information on pages that are applicable to that IP. The entries shown here indicate that the DDR4 hard memory controller IP added 2 PLLs to this page. Next, specify the properties of I/O used in the design. There are many options available, and they are somewhat different between Intel Stratix 10 devices and Intel Agilex devices. We'll look at Intel Stratix 10 device I/O options first. On the I/O page, each row represents all the I/O pins for a particular design module that have all the same properties. These include I/O standard, input termination, current strength, or output termination, depending on whether the pin is an input or an output, data rate, clock frequency, output enable probability, and capacitive load. As always, the hierarchy name can optionally be a path to a lower level design module that connects to the top level I/O. For top level pins that you don't associate with a particular module, set the hierarchy name to just the pipe character, representing the top level. For the application column, select whether the I/O is a GPIO, part of a SerDes, or part of an external memory interface. If the IP wizard was used to create a memory interface, as was the case in the example shown here, the application column will indicate as such for all the different I/O needed to implement the interface. Set the bank type depending on the I/O standard and whether the I/O are part of the hard processor system. If the application column was set to EMIF, the DDR rate column becomes available. Set this to match the clocking relationship between the external memory PHY and the internal user logic, which is also specified in the IP parameter settings for the external memory interface. Available values are full speed, half speed, and quarter speed. Use the number of pins columns to indicate how many input, output, or bidirectional pins a particular row is describing. Differential pin pairs count as only a single pin. Set the SDR/DDR column to single or double data rate, depending on whether the I/O can change state either once or twice per clock cycle. Toggle percentage represents the percentage of clock cycles where the I/O signal toggles, while OE percentage is the percentage of cycles where an output I/O is enabled or a bidirectional I/O is enabled when in output mode. The remaining settings include I/O clocking frequency, internal PHY clock frequency, and settings specific to when the application is set to SerDes. Set these values as appropriate for your design. For Intel Agilex devices, most of the columns are identical to the I/O page for Intel Stratix 10 devices, but there are some important differences. First, for Intel Agilex devices, you can select a bank ID. Just like on the PLL page, setting a bank ID for the use of I/O resources will have an effect on resource utilization and the thermal analysis. Next, instead of specifying the directionality of I/O pins in separate columns, use the number of instances and interface direction columns to set the number and directionality of pins for a particular module that share all the same properties mentioned earlier. The interface rate column is the same as the SDR/DDR column in the Intel Stratix 10 device PTC for memory interfaces, but includes different options such as full, half, or quarter rate depending on the application setting, either GPIO, SerDes, or EMIF. For the EMIF application type, set the number of DQ pins, the number of I/O lanes needed for the DQ pins, and the number of I/O lanes needed for the address and command signals. If you use the IP wizard to add an EMIF IP, all this information is entered automatically based on the IP parameters selected. The remaining columns are identical between both calculators. On the transceivers page, specify transceiver configuration and usage in your design. Once again, there are a number of differences between the Intel Stratix 10 and Intel Agilex versions of this page, so we'll start with the Intel Stratix 10 PTC. Many of the options available depend on the transceiver tile type you're using and the operation mode of the transceiver. E tiles are for gigabit Ethernet applications, P tiles are for PCIe applications, and H and L tiles include general purpose transceivers as well as support for PCIe. Tile options are available depending on the device selected on the main page. At the top of the page, you can select a general option for how unused transceiver dies should factor into the calculation for devices that include H-tiles. Unused H-tile transceiver dies can be active, but in low power modes based on the selected supply voltage, or they can be shut down entirely. Let's go through some of the tile options. First, you can specify the number of channels and the starting channel location on the tile. If the design allows it, spreading out transceiver channels on a tile can be an effective way of reducing thermal hotspots on the device. This can help simplify the device's cooling solution. We'll discuss this a bit later when we talk about thermal analysis, but for more details, see the thermal management training linked to at the end of this training. Also, for E-tiles, you can estimate power usage when a transceiver is in normal or low power mode. Use normal power mode for thermal modeling and regulator sizing, since the board design should be based on maximum power usage. See the E-tile transceiver PHY user guide to learn how to switch a transceiver into low power mode. Specify if and how you are implementing FEC, the protocol for the Ethernet hard IP if applicable, and the data modulation mode. If you're using a device with a P-tile or general purpose tiles, select the appropriate protocol, including PCIe protocols, from the options available. Finally, for H and L tiles, you can set an application, either backplane or chip-to-chip, to automatically set a number of advanced channel options, or select Custom to customize these advanced options for your application. Here is the Intel Agilex device version of the transceivers page. Many of the columns are similar to the Intel Stratix 10 device PTC, but there are a few important differences to highlight. Again, at the top of the page are options for how to manage unused transceivers in the calculation. The options are slightly different from the Intel Stratix 10 PTC, allowing you to completely power down unused transceivers or power up unused transceivers to a non-zero low voltage rail. E-tile and P-tile devices cannot have their transceivers completely powered down, so that option is not available in the example shown here. The final selection provides a low power option if only some channels are in use for a particular transceiver. You can set these partially used transceivers to a non-zero voltage and preserve the unused channels. The number of PMAs option is similar to the number of channels option for Intel Stratix 10 devices. A PMA is a physical medium attachment. PMAs are grouped together in a transceiver bank and must be counted for the power calculation. See the PTC user guide for details on counting PMAs depending on the transceiver tile type. For E-tiles, the digital analog interface width should be set to the width of the bus between the physical coding sublayer, or PCS, found in the Ethernet hard IP, and the associated PMA. For any other columns, see the PTC user guide for details. The hard processor subsystem page is only accessible for editing if you've selected an SoC target device. Enable the HPS system switch option, select the number of CPU cores in use, and choose a benchmark application. The applications are meant to be representative of how hard the processor will be stressed. For Intel Stratix 10 devices, HPS peripherals may become available to add to the PTC for power measurement through the IP wizard, so be sure to go to the wizard and add the peripherals that will be used in the design. Finally, the High Bandwidth Memory, or HBM page, is configured for devices that include HBM memory stacks in the device package. Each row describes the power usage for each physical channel access to a die in an HBM stack. Select the memory stack and the physical channel used to access a particular die in the stack. Recall that each physical channel is divided into two pseudo channels. For Intel Stratix 10 devices, for each pseudo channel, select a traffic pattern as shown here that most closely matches how you expect to access the memory in your design. For Intel Agilex devices, instead of choosing a fixed pattern, you can specify exact percentages of the expected read rate, bandwidth usage, and page hit rate. 3 additional pages are available for supported Intel Agilex devices. An ADC page is available for Intel Agilex devices with A-tile chiplets. The A-tile includes multiple channels of high-speed analog-to-digital converters that can sample in the gigasample range for direct RF applications. The crypto page lets you add information about the use of the hard crypto blocks in certain devices, while you can provide usage information for the hardened network-on-chip IP on the NOC page. The NOC provides high bandwidth access to certain external memory protocols, including HBM2E and DDR5. See the NOC user guide for details on the NOC, including detailed steps on how to use the NOC and RAM pages of the PTC to get an accurate estimation of NOC power use. While resource-specific calculated power output numbers appear on each resource page, the easiest way to view calculated power numbers is with the Power Summary window and the Report page. The Power Summary window displays the power calculated on each of the resource pages and sums them together. This is a quick way of viewing overall power usage of the design. The Report page displays the power usage for each required power rail in the design. Each rail is broken down into multiple values. You can export this or any report on any resource usage page to a .csv file by right-clicking anywhere in the report. The first value displayed for each rail on the report page is static current. This defines the total static power use for the rail. As such, it does not rely on clock frequencies applied to the design and does not include standby power. For Intel Stratix 10 devices only, standby current is reported for certain power rails. As discussed earlier, standby power is similar to static power since it is independent of signal activity, but focuses on the DC bias current consumed by the I/O and the transceiver analog circuitry. Next is dynamic current. For rails that supply power to resources that use dynamic power, this value sums up the power used by those resources on all calculator pages. For Intel Agilex devices, SmartVid current savings are reported. Smart Voltage ID, or SmartVid, is a feature that allows the device to dynamically adjust its own core voltage down to a silicon-specific lower limit based on changes in the operating environment. The value reported here is the total power saved on the rail due to SmartVid. Total current before SmartVid savings is another Intel Stratix 10 device specific value. Instead of displaying total power savings due to SmartVid, this value shows what the total power usage would be using the typical core voltage of the device instead of the SmartVid reduced voltage. This way, you can see what the power swing would be between the typical voltage and the low voltage. The total current output is a calculation of the total power requirements for the rail, including the savings from SmartVid, if the feature is used. If SmartVid is not used or available, this value equals the sum of the static, dynamic, and for Intel Stratix 10 devices, standby power usage for the rail. Finally, the recommended margin, if provided, can help in sizing the regulator for a power rail by calculating a margin based on the ratio between static and dynamic power required for that rail. For the final section of this training, we'll look at how to set up and perform a thermal analysis using the PTC. As discussed, the PTC can perform a thermal analysis that accounts for the supported device's multi-die architectures, providing a breakdown of power between the transceiver tiles and the core die. The tool calculates psi-JC, the thermal resistance factor, for each die specific to your design. A psi-CA value is also reported as a goal for the design of your cooling solution. Remember that the higher the psi-CA value, the simpler the cooling solution you need to implement to meet the thermal requirements of the design. The PTC supports 4 different modes for thermal and associated power calculations. The default mode is to use a constant junction temperature for all dies, which essentially disables the multi-die thermal analysis. The second mode is probably the most common option. In this mode, set the ambient temperature around the device and specify TJ max, a maximum desired junction temperature for any of the dies in the device. The tool will calculate a psi-Ca with the assumption that at least one of the device dies is at the specified TJ max. That means that the numbers provided can be used to create a cooling solution that will keep the junction temperature for any die at or below the specified value. The third mode is almost the opposite of the second mode. Specify a psi-Ca value and the tool will calculate the maximum junction temperature expected for any of the dies with a cooling solution implemented with that value. This will let you know if your cooling solution will sufficiently cool the dies to be at or below a desired maximum junction temperature. The final mode calculates what the ambient temperature around the device will be when a cooling solution with the given psi-Ca is used. You can switch the calculation mode at any time, and the tool will recalculate on the fly. The thermal analysis page is where options for the analysis are set and the calculated values are reported. The options and detailed reporting are enabled on the thermal analysis page by setting the power characteristics option on the main page to maximum. Set the calculation mode at the top to one of the 4 options just mentioned, and enter the appropriate constraints depending on the mode selected. To improve performance while working with the PTC, leave the power characteristics setting at typical, or leave the recalculate mode to manual until you have completed entering in all your design information on the other resource usage pages. This prevents constant recalculation of the thermals while other resource usage pages are being edited. To get an accurate thermal analysis of your design, it is very important to accurately specify the properties of transceiver interfaces you will use. This is done on the transceivers page. Besides the basic settings such as operation mode, data rate, and voltage, you can also specify the transceiver tile type if multiple tile types are available on your targeted device, and the transceiver die where the interface will be located. The diagram on the left illustrates the placement and naming of the transceiver dies around the core die in a typical device. Once you've selected a die, specify the number of channels or PMAs used by each interface along with the starting channel location. An example of channel numbering for a particular die is shown on the right. The channels used for each interface on a particular die cannot overlap. Set the number of channels and starting channel location appropriately to avoid overlap. Providing die-specific transceiver use information is critical in performing an accurate multi-die thermal analysis. As you edit values in the PTC, make sure to look at the warnings and errors window in the tool to see if there are any errors with any of the settings you have selected, such as overlapping transceiver interfaces, before going to the thermal analysis page for the final results. Here's a closer look at the thermal analysis settings on the thermal analysis page. Depending on the calculation mode, different options to set are available, such as the ambient temperature and TJ max. The PTC reports thermal values based off these settings, with the assumption that at least one of the device dies is at the specified TJ max. That means that the numbers provided can be used to create a cooling solution that will keep the junction temperature for any die at or below the specified value. Optionally, you can enable an added margin of up to 25% on the calculated values. Note that this margin only applies to the thermal values calculated on the thermal analysis page. The values on all other pages do not display this added margin. The final option to highlight is the TSD mode. This option, for Intel Stratix 10 devices only, enables temperature sensing diode, or TSD, offset calculations. Each die, including the core, includes a temperature sensing diode. However, the TSD may not be located exactly at the location of a temperature hotspot. Adding the offset to the value reported by the TSD for a particular die provides an accurate value for that die's junction temperature. You can choose to calculate this offset based on the on-chip digital thermal sensors, or DTS, or off-chip TSD components. Let's look at these TSD offsets in a little more detail. By adding the temperature sensor Intel FPGA IP to a design, you can read out the temperatures reported by each DTS on the core die and each of the transceiver dies. The heat map shown here illustrates how the sensors may not be located exactly at the hotspot on a particular die. With the TSD offset values calculated by the PTC, you can include them directly in your design so that readings from the sensors are accurate. However, note that these offsets and the other thermal calculations are unique for each design implementation. If any changes are made to the design, you would need to recalculate all the thermal parameters in the PTC, including the TSD offsets. Based on the values entered in all the pages of the tool, the thermal parameters discussed earlier are calculated and displayed on the thermal analysis page in the solution table. The analysis shown here is for Intel Stratix 10 devices. The analysis is different for Intel Agilex devices and will be shown in a moment. Here you can see a breakdown of power usage and SiJC for each die, including the core and an HBM if applicable. A recommended SiCA is also displayed. In the example shown, transceiver tile 2.1 uses the most power, but tile 2.0 has the highest SiJC. The cooling solution should be designed to account for this, or the transceiver design and placement could be adjusted. For Intel Stratix 10 devices, the TSD offset calculations are also displayed here. As just described, the offset value represents the difference in temperature between the hotspot on the die and the location of the sensor itself. Adding the offset to the value reported by the TSD for a particular die provides an accurate value for that die's junction temperature. The solution table is used as a summary of the calculated thermal values, as well as what the values would be if the core junction temperature was 5 degrees above or 5 degrees below its calculated value. No temperatures in the solution table should exceed the values shown in the maximum junction row of the table. Note that even if the temperatures in the middle column do not exceed TJ max, at least one die may exceed TJ max in the plus 5 degrees column. As such, the plus 5 degrees column should only be used as an analysis metric and not as a basis for the cooling solution. The variance in core junction temperatures reported can also be used to create a temperature-dependent core die power curve. This is often used by computational fluid dynamics, or CFD tools, when analyzing airflow and cooling solutions. The thermal analysis for Intel Agilex devices is a bit different. On the left side of the thermal analysis page, the overall maximum SiJC for all dies and recommended ambient temperature and recommended SiCA for the cooling solution are displayed. Again, these are based on the calculation mode selected and the constraint value supplied. There is no breakdown of SiJC for individual dies. On the top right of the page is the thermal margin report. This report is broken down by dies, including the core. The temperature and power margins in the table indicate the amount of margin there is for that particular die before the design would hit the maximum junction temperature that was specified in the input constraints. On the lower right is the temperature target report table. Each die, including the core, includes one or more digital thermal sensors or thermal diodes. This table indicates the temperature that would be seen on each of those monitors while the design is running and using the resources specified on all the resource usage pages. Note that the monitors are not necessarily located at the hottest spot for a particular die, and there is no offset calculated for Intel Agilex devices like there is for Intel Stratix 10 devices. This concludes the training. For more information, we recommend the linked documents listed here. Start with the PTC user guide for detailed information about all the settings and options available in the tool. The Intel Quartus Prime software user guide on power analysis and optimization, and the Intel Agilex and Intel Stratix 10 power management user guides should be your go-to references for power management. If you are using a device that includes the hardened network-on-chip IP, such as the Intel Agilex 7 FPGA M series, the NOC user guide details its use and provides a recommended flow for using the PTC to estimate NOC power usage. Other documents are available for power analysis and optimization in older device families. 2 white papers provide more detail about how power analysis works in general in an FPGA device. These are older documents, but they cover the basics of FPGA power analysis and are still applicable to current devices. Finally, you can find links to these documents and others at the Power Solutions Support Center on the Intel website. Intel offers many options for learning about our FPGA products and for training on their use. The Intel FPGA YouTube channel contains a number of 5-minute quick videos along with longer, more in-depth training. The Intel FPGA training website is the place to go to learn about our recommended learning plans for every type of user and to register for a class. While there, you can register for over 300 e-learning courses made up of narrated slides presented in an interactive player, some of which include labs and demos. You can also register for one of our full-day instructor-led training classes taught by experienced training engineers, either in person at a local office or virtually over the web. All instructor-led courses have hands-on lab exercises to practice the concepts you learn. If you need further assistance, Intel FPGA provides many self-help resources. Check out the landing pages accessed from the main Intel website that are dedicated to specific FPGA technologies like high-speed interfaces and external memory. Finally, you can also view and post questions to the community forum, monitored by skilled Intel FPGA application engineers. One more thing. When you registered for this e-learning, you should have received a link to a short survey where you can provide feedback. We'd greatly appreciate it if you'd fill out that survey now. We're constantly updating and improving our training materials, and your feedback helps us create the materials that you want. Thank you for your feedback. My name is Steve, and I want to thank you for taking this training about the Intel FPGA Power and Thermal Calculator.